So what could we use, what quantity could we use for this chemical potential to predict spontaneity? Remember enthalpy? That's a Chem 1A topic. So enthalpy was capital H. And it's really the change in energy at constant pressure. Okay, so as long as the pressure is constant. So anything open to the atmosphere, delta H is going to be the change in energy. So it's Q at constant pressure. So delta H being positive was an endothermic reaction, and delta H being negative was an exothermic reaction. Heat or energy coming in or going out, right? So if we used enthalpy as our chemical potential, that would predict that all exothermic reactions are spontaneous and all endothermic reactions are not spontaneous. But that's not true, because some endothermic reactions are spontaneous. A chemical cold pack, one of those instant cold packs you have in a bag at the baseball game or whatever in case somebody gets hit in the face, right? You break the little seal inside, you mix the stuff together by squishing it, and it gets cold. It's an endothermic reaction of probably the ammonium, I think it's ammonium nitrate, dissolving in water. And as it dissolves in the water, it absorbs energy from the surroundings, making it cold. But it's spontaneous. You don't have to do anything. You don't have to hook up a battery to make it do that. So why? Well, enthalpy's not our guy here. A couple other examples of spontaneous processes that involve an increase in enthalpy. So enthalpy does not predict that this would occur. The melting of ice above 0 degrees Celsius. So we actually have some ice here. There's an ice cube. 2 ice cubes. They are above 0 degrees Celsius. What's going to happen to them? They're going to melt.
Phase change.
Yeah, phase change, solid to liquid. Is that endothermic or exothermic? Endothermic. Because it's absorbing energy to melt. Enthalpy predicts that that's not spontaneous, and yet it is. Evaporation of liquid water to gaseous water. So after these ice cubes melt, they're leaving a little puddle there in the dusty surface. What's going to happen to the water? It's going to evaporate. It's going to go into the gas state. Also an endothermic process, but spontaneous. Sodium chloride dissolving in water. Also spontaneous and endothermic. So what's in common? They are endothermic and they're spontaneous. What else is similar about these things? Entropy, yeah. So here we have water in the solid state. Frozen water is crystalline. The water molecules line up in very specific ways. That's why snowflakes are so beautiful. And when that melts, what happens to the order of those water molecules? It goes away. They become very disordered, right? And when liquid water, where all the particles are at least close together, becomes a gas, they also increase in disorder. They spread out. Same thing happens with salt dissolving. Right here we've got our salt crystal. Everything's all lined up. Sodium, chlorine. And then when it dissolves, it spreads out, becomes more disordered. So in each of these processes, disorder or randomness is increasing. So entropy is the criteria we need for spontaneity. The easiest way to think of this is that entropy represents disorder or randomness. We'll understand that it's actually a little bit more specific than that. But I tell people my house is a demonstration of entropy, right? Spontaneous process, right? Unless you continually put energy in, it just goes to heck, right? There are clothes everywhere. I sometimes think, we decorated an early frat house. There's plastic cups and dirty underwear all over the place. Of course, having 5 sons doesn't help, but disorder. You think of a tree in the fall. The leaves are on the tree, and they're pretty organized, right? Trees have definite structures of where the leaves are. And then fall comes, and the leaves turn pretty colors, and then they fall off the tree. And do they fall into neat piles? No, they go all over the place, right? 52-card pickup. Take a deck of cards and toss it in the air. Do they land all organized? No, they go all over the place. Entropy, positive entropy. So entropy is a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. So that's why it's easier to think of as disorder. So entropy is given the symbol S. There's only so many E's you can have, right? So S is equal to a constant times the natural log of W. This constant has a name. It's the Boltzmann constant. It's equal to the ideal gas constant divided by Avogadro's number. So there's a couple of familiar values there. And when you do the units on that, you end up with joules per Kelvin. W is the number of energetically equivalent ways to arrange the components of the system. And we're going to look at some simple examples so that we can understand that. But because W is just a number, and we've got the natural log of it, the units on entropy come from the Boltzmann constant, and so they are joules per Kelvin. So entropy is units of joules per Kelvin. Yeah?
So W is a measurement of the disorder?
Yeah, W is a measurement of the disorder of a system. But specifically, it's the number of energetically equivalent ways that the components can be. So that's probably a bit confusing. So let's imagine we have a fixed amount of an ideal gas, and the pressure's constant, the volume constant, and the temperature is constant. The moles is constant. So everything's constant, right? So the state of that system is defined by pressure, volume, and temperature. And so the energy of that system is going to be constant. If we change the temperature, then we're going to change the energy, but we're not changing anything. It's just got this fixed thing. So we can call that a macro state. So the energy of the system is constant, but what are the individual gas particles doing? They are moving, right? Kinetic molecular theory of gases. Gas particles move in straight lines until they run into something and they bounce off. They don't interact with each other, and they don't lose energy when they collide. So the energy of any given particle is not constant, but overall, the energy of the gas is constant. You okay with that? So we can have a particle that has very high kinetic energy, but it might bump into another particle and transfer almost all of its kinetic energy to that particle, and now that first particle is low in kinetic energy. But overall, the energy of the system is constant. That's the macro state. Total energy is constant. A micro state, we're looking inside, we're looking smaller, and that could be represented as like a snapshot of the exact internal energy distribution among the particles. So you could imagine, a bunch of elementary school children at recess, right? And some of them are hanging around, and some of them are running and jumping and doing things, right? So if you took a picture and froze that in time, you could say, well, that kid was moving at this velocity, he had this much kinetic energy, and this person was standing still, they had almost zero kinetic energy. And you could look at instantaneously what was each of the particles doing. So the macro state, that total quantity of energy, can arise from a lot of different microstates. Exactly where the energy is distributed among the particles does not affect the macro state, the overall total energy of that gas. And so we can think of W as the number of possible microstates that could result in the given macro state. So now we're going to take it to very simple. 2 particles. Can't get much simpler than that. So we're going to look at 2 different systems. They each have 2 particles with a total energy of 4 joules. So here's system A. We have a red particle and a blue particle. And in this system, there's only one energy level that's possible. And so the blue and the red they have the same energy. They both have 2 joules of energy. System B, the same macro state, a total of 4 joules of energy, but this system has 2 different levels. And so there's a 3 joule level and a 1 joule level. So in this microstate, we have the blue one at 1 joule and the red one at 3 joules. But there's another possible microstate where you have the blue one at the higher energy and the red one at the lower. So these 2 microstates are different in that different particles have different energies. Does that make sense? Here the red particle has 3 joules of energy in this microstate. Over here it only has 1 joule. That's different. But if you look at the macro state, you add the energy of all the particles together, it's the same. So system B would have W equals 2. System A, W equals 1. There's only one possible state. All the particles have the same energy. There's no variation. So which system has more entropy? System B. Because entropy is the Boltzmann constant times the natural log of W. Well, if this has a W equal to 2 and this is W equals 1, this is going to have greater entropy, system B. Any questions about that? Because if we have questions about that, we're going to have questions about the next step. So entropy of a state increases with the number of energetically equivalent ways in which the components can be arranged to achieve that. The state that has the highest entropy also has the greatest dispersal or spread of energy. So in system B, the energy was dispersed or spread out over 2 different levels, whereas in system A, all of the energy was in one place in one level. So a state in which a given amount of energy is more highly dispersed or highly randomized has more entropy than a state in which the same energy is more highly concentrated. So entropy also comes out to being a measure of the spread of energy. Which brings us to the official statement of the second law of thermodynamics. For any spontaneous process, the entropy of the universe increases. Not necessarily the energy of the system, but entropy of the system, but the entropy of the universe increases. So delta S for the universe is greater than 0. That is how we determine if something's going to be spontaneous or not. So entropy is a state function. Remember what a state function is? It depends on the final state and the initial state, and not on how you get there. So it's kind of interesting because I just went over this stuff in Chem 1A, and so I have to remind myself that you guys weren't in there. So he gives this analogy. That's a mountain. It maybe doesn't look much like a mountain. And there's 2 paths that you can take to the top of the mountain. You can climb straight up or you can take this path that wiggles around. Your change in elevation from down here to the top of the mountain is going to be the same regardless of which path you took. The change in elevation is the same, right? Change in elevation is a state function. Doesn't matter how you got there. It's just the difference between where you started and where you end up. The distance that you travel on this hike, though, is not a state function. It does depend on how you got there. Does that make sense? The distance between two objects is a state function, but the distance traveled going from one object to another is not a state function. So my house is about 30 miles from Fresno City College. So I can get there several different ways, right? I have my favorite, but there are other ways. I usually try to go one of the shorter ways. So I'm going to, head southeast. What if I head northwest and go around the planet? Could I get to my house? I could. Take a long time, be expensive. I travel much, much farther. If I did that, the difference from where I started to where I ended up would be the same, but the distance traveled would be very different. That make sense? So state function only depends on the final and the initial state, not on how you got there. Entropy is a state function. Let's look at another chemical system. A little more complicated, but not too bad. So what we see is that a chemical system will proceed in a way that will increase the entropy of the universe. So we're going to look at an ideal gas. Here it is contained in this flask, and we've got a stopcock here, and over here is nothing. It's a vacuum. So intuitively, what do we know is going to happen when we open the stopcock? The gas is going to spread out, right? Is it all going to go over here and stay over here? No. It's going to spread out and be pretty much evenly distributed between those two flasks, right? So here we have a gas. It's expanding, right? Its volume is changing. And there's a type of work called pressure volume work, where that work is equal to negative P delta V. So expanding a gas against a pressure is a form of work. Here there's no pressure. It's expanding but not against a pressure, so there's no work, so there's no energy change. So no energy change is involved. The only thing that's changing here is the entropy. So before we open the stopcock, we only have one possibility. We have the four particles in the left container, right? It's only one state. When we open it, there's several different possibilities. We're just going to look at three of them. You could have all four particles on the left, all four particles on the right, or you could have them split, 2 on one side, 2 on the other. So three microstates. Well, three macrostates that we're going to look at, and then we're going to look at microstates for each of these. Let's go back. Oh, wait. Yeah, I skipped this. I'm like, there's something missing. There was something missing. So we're going to number the particles 1 through 4 because different particles are different particles, even if they are the same kind of atom. So for state A, you can have all 4 particles on the left side or nothing, right? All 4 particles on the left side, that's all that you can have. There's one microstate. For state B, you can have all 4 particles on the right side, and that's the only possibility. That make sense? For state C, where we have 2 particles on the left and 2 on the right, we actually have 6 different microstates. So we could have 1 and 2 on the left, 3 and 4 on the right, or this one down here is the exact opposite of that. Same pairs, but opposite sides. We have 1 and 3 on the left, 2 and 4 on the right, or the opposite of that. We could have 1 and 4 on the left, 2 and 3 on the right, or the opposite of that one. So there's 6 different possibilities of where these could be. 6 microstates versus 1 microstate. Which state has higher entropy? State C. The probability of finding atoms in state C is 6 times greater than in state A or state B. If we go from 4 particles to 20, now there's 184,756 microstates for state C, which would be equal numbers of atoms on each side. What's the number of microstates for A or B? It's still 1. All the particles on the left or all the particles on the right, there's still just the 1 microstate. So if we go from state A, let's go back to this one. If we go from state A to state C, the number of microstates increases significantly. The entropy is positive. The final amount of entropy minus the initial amount of entropy is positive. Positive change in entropy is a spontaneous process. So delta S, delta we almost always use as the final minus the initial. Delta S is the entropy of the final state minus the entropy of the initial state. Now, actually measuring the quantity of entropy is pretty hard. It's like measuring absolute energy. You need a reference point, and it's really, really complicated. And so we're usually interested in change. The change in the entropy, the change in energy, the change in the temperature. When all those atoms are confined to 1 flask, their energy is also confined to 1 flask. And when we let the particles expand and spread out over the 2 flasks, now their energy is also spread out over 2 flasks. And so the energy is spread out, the energy is dispersed. Does that make sense? Oh, look, the ice cube's gone. Oh, there's a puddle. So, second law of thermodynamics is going to explain some of these things that were not explained by the first law. So why do ice cubes melt? The heat from the water travels into the ice cubes, and the temperature goes to the same temperature, right? The water cools down. Eventually, the ice would heat up, and it would come to a common temperature. It never happens that you take ice and throw it into water, and the ice gets colder and the water gets hotter. That never happens, does it? Because that would involve separating energy. So this is an increase in entropy because the energy which was in the water is now spreading, expanding into the ice. So the energy is being dispersed. That's a natural, spontaneous process, not energy becoming more concentrated. If you think of the playing cards, right? Them spreading around when you throw the deck in the air, they are spreading their energy. To concentrate their energy, you have to expend energy and go pick them all up and gather them together. And that would be concentrating the energy of the playing cards.